Hello, everyone. Today we're going to go through the chapter 2.3.2, which is the method of images. We're going to go through some specific cases. Um, you will see those cases. In those cases, when you try to solve the problems for some distributed charges, for regular method, it's very difficult to solve the problem. However, sometimes if you change your solution by not considering the original charge distribution, instead, you create another situation which may have the same solution as the original problem, then that solution could be used as your in your problem. And in this case, we need to use some image charges. Now, let's see the first problem, which is a very classical problem, the classic image problem. Now, let's see a situation. Suppose a point charge Q is held in a distance d above an infinity grounded conducting plate. Now let's see this figure. You have a charge Q here, and then you have a plate which is infinity large. It's a big plane, and it's a conductor. So now the question is, what's the potential in the region above the plane? It seems like to be very complicated. First, this is x, y, z coordinates. If we look into the against the x direction, what you see is you will have a large, let's say, a very large plane or a plate, and you have a Q, which is here. And then, first of all, if I ask you, what's the potential distribution and what's the electric field lines? So first of all, for the potential distribution, it clearly said in the textbook. So when z equals to 0, let's say this is z coordinates, and this is 0. 0 means on the plane. When z equal to 0, then v should be 0 because it's grounded. Let's say it's grounded. This means grounded. So the potential here is 0. And then when when the position is far away or infinitely far, then the potential should be 0. Now let's see another situation. If we draw the electric field lines, what you might see is something like that. Because it's an infinity large plane, so you have infinity numbers of the field lines, but for each field line, when it's going to the plane, it's always perpendicular to the plane because it's a conductor. You can imagine that if it's not perpendicular to the plane, then the charge, the induced charge, will move on the plane until it's perpendicular. Then the charge doesn't have any, the induced charge doesn't have any component in the, let's say, y direction. Let's say this is a y direction. It doesn't have, let's put it in the slides. It doesn't have any components in y direction to move the charge along the plane. So because this is a positive charge putting above the plane, so there should be a lot of negatively induced charge distributed on the upper surface of the airplane. So that's the electric field distribution. Okay. Now, so because we want to calculate the potential, or V, in the above region, or in the region above the plane, so it's not just the Coulombic equation, because Q will induce a certain amount of negative charge, as I showed here on the conductor surface. Then the total potential is due in part to Q. So the potential, let's say at any place here, the potential is due to the charge Q, but it's also due to the induced charge. But how can we possibly calculate the potential? Because it's difficult to know how much the induced charge is distributed on the plane, and how is it distributed. Of course, it's not a uniform distribution. But at least we know these two conditions, or the boundary conditions. Number one, when z equals to 0, we know the potential is 0. And then when v is far away, or infinitely far away from the charge, the potential is 0. Now we have the boundary conditions. Then the problems could become simpler if we consider in another situation is if we think about another case, let's forget about the actual problem. We're going to study a completely different situation. This new configuration consists of 2-point charges, plus Q at D and negative Q at negative D, which is below the conductor plane, and no conducting plane. For this configurations, I can easily write down the potential. Okay, now let's forget about the real situation, which is a charge, and then you have a conductor, as I shown here. Let's consider about another situation, which is a charge here plus Q. This is y-axis, sorry. This is y-axis, and this is z-axis. Let me change the size of the pen. Now, if you put another charge, which is negative Q here, then what happens? If you have a plus Q above and a negative Q below the plane, the y plane, the y-axis, and the distance is d here and d here. They have the same distance. Then in this case, we don't have any conductor plane. Then in this case, you still get the two conditions, boundary conditions. First, when z equals to 0, or in the y-axis, the v is 0. Suppose you have a point charge here. If you calculate, let's say, if you try to calculate the potential generated by the plus Q and potential generated by the negative Q due to the symmetry condition. The potential here, or anywhere along the y-axis, or when z equals 0, the potential should be 0. And in another case, when you consider the point is far away from your charge plus Q, which is infinite far away from Q, the potential, of course, is still it's 0. Then see, in this situation, it has the same boundary condition with this situation. Then in order to calculate the potential above the plane, we don't have to really consider the conductor. What we can do is we can just replace the conductor by another charge, which is negative Q here. It's called an image charge. If you calculate the situation in this case, you will have the same potential as the previous case when there's a conductor. Now, let's look at the field lines. If you look at the field line should be the same. That's the field line. If there's no conductor, the field line looks like this. It's, if we look at the, of course, below the plane, you will have field line like that. If we look at the situation which is above the plane or above y-axis, then the field line is exactly the same as in this situation. And the condition is also the same, boundary condition is also the same, and the charge distribution above the plane is exactly the same. So based on the uniqueness theorem, you should have the same solution in the upper space in this situation compared to the previous situation. Then now in this situation, it's very easy to solve the problem. If you ask to calculate the, let's say, the potential above the plane, let's say here. So the potential is generated by plus Q and negative Q in these two locations. Then V equals to 1 over 4 pi epsilon Q over the distance between positive Q and your location subtracted by Q over the distance between negative charge and your location, your concerned location. Then it becomes very easy. So this is due to the uniqueness theorem. If you have the same boundary condition and you also actually have the same charge distribution in the upper plane, then you should have the same solution, no matter in this case or in that case. Or in other words, let's try to understand this situation in this way. If you put a conductor here, then the conductor generated a lot of surface charges. And those surface charges makes the electric field lines distributed in this way. That's the effect of the induced charges. And you can consider if you remove the conductor and replace it by another charge, which is shown here. This charge will generate exactly the same electric field lines or potentials in the upper plane. So this negative charge is the image charge, or this image charge is effectively equal to the induced charges on the surface. So effectively, those two set of charges, they are the same, or their effect are the same. So you can see by changing the situation, you get a very easy solution to solve such problems. Okay. The crucial role played by the uniqueness theorem in this argument is, without it, no one would believe this solution, since it was obtained from a completely different charge distribution. But the uniqueness theorem certifies it if it satisfies the Poisson equation in the region of interest and assumes correct value at the boundaries, then it must be right. Or in other words, the solution for this case and the previous case should be exactly the same. Okay. Now we have calculated the potential, which is shown here. Now let's continue to calculate some other features. So first, let's calculate the induced surface charge. Now we know the potential, then it's a straightforward to calculate the surface charge, actually, or the surface charge density induced on the conductor. If you go back to the equation 2.49, then you can use the equation to calculate the surface charge. Actually, the surface charge density, which is sigma equals to negative epsilon partial v over partial z, and v equals to 0. And from the previous equation shown here, which is 3.9, this is the potential distribution. Then partial v, v is equation of z, then partial v over partial z, you can get the derivative to be shown here. So sigma equals to this equation. As expected, the induced charge is negative, and the greatest value is at when x equals to y equals to 0, which is just below the positive charge. And when it's moving to the left or right, then the induced charge becomes weaker. While we're at it, let's compute the total induced charge. Now you have the surface charge distribution. Now surface charge density distribution. Now let's use the density to calculate the total charge, which is of course a surface integral. And then the surface integral could be written in this way: a surface integral of the surface charge density times dA, and surface charge density could be written in not in Cartesian coordinates, but in polar coordinates, because in polar coordinates the integral becomes easier. And in polar coordinates, we have learned dA equals to r times dr d phi. Then your surface integral becomes in this situation, and it's easier to be calculated, and finally your charge should be negative q. So the total charge induced on the plane is, again, it's negative q. As you can perhaps convince yourself, it had to be. So if you think about the two situations, this situation, in this situation, you have a negative Q here without any planes or conductor plane. In this situation, you just distribute a negative Q along an infinitely large plane and distribute it in a specific way that it effectively equals to you put a negative charge here. So that's the total charge on the plane, the total induced charge on the plane. Okay, after the charge calculation, let's see the force and energy. So the force is easily to be calculated because now you have a charge which is plus Q here. This is the XY plane, and you have a charge negative Q here. You want to calculate the force in the upper plane. It's very easy. So you can calculate the force generated by this Q and the force generated by the negative Q by using Coulombic equation. Then finally you will get the force to be here. We don't write down the two terms generated by plus Q and negative Q. It's very easy. Please do it by yourself, and you get the final force shown here. Now let's see the energy. So far, everything is the same in the two situations, no matter it's a potential or surface or the force, they're the same. However, for the energy in two situations, the energy is different. It's easy to get carried away and assume that everything is the same in the two situations. However, energy is not the same. So with a 2-point charge and no conductor, 2.42 gives you the way to calculate the energy. So energy equals to this equation. But for a single charge and no conducting plane, the energy is half of this energy, which is shown here, based on the previous equation 2.42. So why in the single charge and conducting plane situation, the energy is half? So think about the energy stored in the field, which is shown in this equation. In the first case, both the upper region and the lower region contribute by symmetry. They contribute equally. But in the second case, only the upper region contains a non-zero field. So the energy is half as great. So this conclusion is directly calculated from the equation 2.42. Remember that in the conductor situation, the energy is halved because there's only one charge above the plane. But in the second situation, or in the two charge situation, the energy is doubled because actually you really have two charges in the upper and the lower region, and the field lines are different. The field lines for the one charge situation, you have field lines in the upper region, but no field lines below. However, in the two charge situation, you have field lines above and below the XY plane. So the energy is different. And of course, we can calculate the energy by calculating the work required to bring Q in form, bring Q to your concerned position from infinity. The force required can be calculated using the equation 3.12, which is shown here. This is the force. So the work can be calculated by an integral from infinitely far away position to your position, which is concerned, let's say the distance between your position and the origin is d, then this integral of f dot dl. It's a line integral, and then by solving this integral, finally you will get the solution to be 1 over 4 pi epsilon q squared over 4d. So as we move q toward the conductor, we do work only on q. It's true that induced charge is moving or is moving in over the conductor, but this costs nothing since the whole conductor is at zero potential. By contrast, if we simultaneously bring 2-point charges with no conductors, then we have to do work on both of them, and the total is twice as great. Okay, so that's the work. So we have finished the classic problem, which is putting one charge above an infinitely large conductor plane, and how to calculate the potential or electric field or energy force in the upper region. It equals to you put another charge below, or you put a image charge below the plane, and then things becomes very easy. And sometimes you have other situations which can be much easier if you have an image charge. So let's see some other image problems. The method just described is not limited to a single point charge. So any stationary charge distribution near a ground conducting the plane can be treated in the same way by inducing its mirror charge or mirror image charge. Hence the name method of images. Remember that the image charge has the opposite sign. This is what guarantees that the xy plane will be at potential zero. There are also some exotic problems that can be handled in similar fashion. And the nicest of these is the following. Now let's see another different situation. A point charge Q is situated a distance a from a center of grounded conducting sphere of radius r, which is shown here. You have a sphere radius, which is radius r, and it's let's say it's conductor, and it might have some induced charge distributed on the surface. And now you have a charge Q, which is in a distance of a away from this surface. Find the potential outside the sphere. Okay, so in this case, you will have some image or induced charges on the surface, but it's very difficult to calculate what's the distribution of those charges. However, there's another way to solve the problem, which is examine a completely different configuration consisting of the point charge Q together with another charge, which is Q prime. Q prime equals to negative R over A times Q. Place this charge in a distance B equals to R squared over A to the right of the center of the surface, and then remove the conductor. Now, there is no conductor, there are only 2-point charges. The potential of this configuration is the same. And here shows the situation. Now, remove this conductor. Instead, put another charge Q prime at a distance of B. The magnitude of the Q prime and magnitude of B can be calculated using these two equations, and then you should have the same electrostatic distribution, or let's say electrostatic potential or field lines, forces at everywhere outside the surface region. So this is the situation for a surface or a sphere conductor. If you have a sphere conductor, then you can replace this conductor by this charge and put it at some specific location. Okay, so if you have those situations, if you have those charges, Q prime and Q here, then it's very easy to calculate the potential at any position. Let's say if you want to calculate the potential here, then you can calculate the distance between here and Q, and also the distance between here and Q prime. Let's say it's R and R prime. Then your potential will equal to 1 over 4 pi R, of course, Q over R plus Q prime over R prime. Now it happens that this potential vanishes at all points on the sphere, and therefore it fits the boundary condition for our original problem in the exterior region. And the previous equation is the potential of a point charge near a grounded conducting sphere. Notice that B is less than R, so image charge Q prime is safely inside the sphere. And you cannot put image charge in the region where you are calculating V, because that would change the charge distribution, and you will be solving Paulson's equation with the wrong source. In particular, the force of attraction between the charge and the sphere is calculating using this equation. Okay, the method of images is delightfully simple when it works, but it is as much as art as a science, for you must somehow think up just the right auxiliary configuration, and for most shapes, this forbiddingly complicated, if not possible. Okay, in other words, this is a very good method, but it happens when there's some special symmetry. For example, you have a charge over a conductor plane. Then this is a very good symmetry for the image charge to work. If not, let's say, if not a simple case or some easy case like that, sometimes it's, most of the times, it's difficult to find a simple image charge or a set of image charges to replace the original conductor. So, this method works very well if in the situation it could be used. However, if in a situation it cannot be worked, and that's most of the cases, then still we cannot use this method. We have to do complicated calculations. But in this chapter, we'll have some problems for you to solve, which can be considered in this situation. You can use a simple image charge or a set of image charges, which can simplify the equation or the problem significantly. Okay, so that's all for this chapter. Not this chapter, but this section. I'll see you in next class. Thank you.